What if the world did not decide its properties until we looked at it?
Welcome. This is a short journey into the surprising rules of the tiny world. This is the world of quantum physics. In the next 8 to 10 minutes, you will meet strange ideas that changed how we think about reality. You will see simple experiments and stories. You will learn why tiny particles behave in ways that seem impossible and why that matters for the future.
Let us begin with the history. In the 19th century and early 20th century, scientists discovered things they could not explain with old rules. Light sometimes behaved like a wave. Sometimes it behaved like a particle. Electrons sometimes behaved like particles. Sometimes they behaved like waves. These facts shook the world of physics.
One early step came from a man named Max Planck. He started the idea that energy comes in tiny bundles. He called them quanta. That idea grew into a new theory. We now call it quantum physics. Albert Einstein helped build this theory, yet he felt uncomfortable. He thought the theory might be incomplete. He wished for a clearer, more classical picture of reality.
One clear experiment that helped create quantum physics is the photoelectric effect. Shine light on a metal and electrons jump out. This happens only if the light has enough energy. This showed that light can act like a particle. Simple experiments like this taught scientists that the small world does not follow the rules we see every day.
A deeper mystery is the double slit experiment. Imagine shooting single particles through two narrow slits. If we do not check which slit a particle goes through, we see a pattern like waves. The particles interfere with themselves. If we check which slit the particle passes, the wave pattern disappears. The act of measuring changes the outcome. This is one of the clearest signs that quantum systems do not have fixed answers before measurement.
To explain this, many people used an analogy. Imagine you have two matching gloves, one left, one right. You put each glove in its own box and send the boxes far apart. Open one box and you instantly know the other glove. There is nothing spooky here. The gloves knew their states all along. But quantum particles can show correlations that cannot be explained by hidden, pre-existing answers like the gloves. That is the heart of the puzzle.
In 1935, Einstein and two colleagues challenged the new theory. They showed a thought experiment that argued quantum physics might be incomplete. They imagined a situation where two particles are linked or entangled. Measure one and you instantaneously know something about the other. Einstein called it spooky action at a distance.
For decades, this remained a philosophical debate. Then, in 1965, John Bell changed the game. He found a test. Bell wrote a mathematical inequality. If the world follows local realism, the inequality must hold. If quantum physics is right, the inequality can be broken. For the first time, the question moved from philosophy to experiment.
A typical Bell test uses pairs of particles sent to two distant stations. At each station, the experimenter chooses a setting. Then, detectors record a result. Repeat this many times. Compare the correlations between results. If the correlations exceed the limit given by Bell, local realism fails. If they do not, local realism could still be true.
Real experiments are not perfect.
detectors miss some particles. Some choices might not be truly random. Early experiments had such weaknesses. These are called loopholes. Scientists worked for decades to close these loopholes. Still, the experiments of the 1970s and later gave strong evidence for quantum predictions. They showed correlations that local realistic ideas could not easily explain.
What is entanglement in plain words? Entanglement means two or more particles are part of a single whole. You cannot describe one without the other. Measure one particle and the possible outcomes for the other change instantly. Yet no usable signal travels faster than light. The randomness of each outcome prevents faster-than-light messaging. Entanglement is a real connection, but not a way to send messages.
Why does this matter? Because entanglement is not only a curiosity, it is a resource. Scientists use it for ultra-secure communication called quantum cryptography. Engineers use it to build precise sensors, and it is central to quantum computers that could solve some problems much faster than classical machines. All these ideas stand on the strange rules of the quantum world. Let us recap with 3 simple experiments and ideas. First, the photoelectric effect showed light behaves like a particle. Second, the double slit showed particles can act like waves when unobserved. Third, Bell tests showed that the strongest correlations in nature cannot be explained by local hidden variables. These 3 results formed the pillars of quantum strangeness.
A few common confusions deserve a quick answer. No, quantum effects do not let you send information faster than light. Causality is safe. No, quantum weirdness does not mean our minds create reality. It means that the properties of a quantum system do not exist in the same definite way as macroscopic objects until measurement. And yes, the quantum rules apply to the whole universe. But decoherence, the loss of quantum coherence, hides these effects in everyday life. Decoherence is a key idea. Tiny quantum states are fragile. They interact with the environment. These interactions wash out quantum behavior. That is why we do not observe superposition or entanglement in large objects. This is also why building quantum computers is hard. We must isolate quantum systems and control their environment. Quantum physics changes how we think about nature. It asks us to accept that the world at its smallest scales follows rules that defy everyday intuition. But these rules also give us new power. They let us build better technologies and ask bolder questions about reality. Thank you for watching. If you enjoyed this short journey, share it with someone who loves a good puzzle. If you want a deeper look, watch more videos about experiments like the double slit, Bell tests, and the modern demonstrations of entanglement. The story of quantum physics is still unfolding, and you are part of the next chapters. The tiny world may be strange, but it is opening doors to a future we are only beginning to imagine.